To learn more about earning college credits with study hall courses, check out gostudyhall.com or click the link in the description. Dealing with massive quantities of data is a big deal right now. But actually, it's nothing new. Like, as early as 1880, the population of the United States was about 50 million, large enough that the Census Office couldn't finish processing the data before the next census started in 1890. That means it would have taken them more than 10 years. But by the time of the 1890 census, that process had sped way up, and that was thanks to the inventor Herman Hollerith, who created a mechanical tabulator, a machine which massively sped up the process of adding up the numbers, so data from the census could be processed before work on the next census needed to begin. Today, computers have taken data processing to a whole new level and can process trillions of numbers in seconds. Now, whether we're calculating how much food we need for a party or we're working out interest rates for an entire economy, manipulating data is at the heart of how we understand the world and make decisions. But just like back in the 1880s, we can't tackle all of this data alone. We need the efficiency of computers. And in programming, one way we get computers to put this data crunching power to good use is with expressions. I'm Sabrina Cruz, and this is Study Hall, Code and Programming for Beginners. Before we get too caught up in the action, we need to talk more about what we're working with. Basically, the different types of data we might want to do something with, because the form of our data limits what we can do with it. Like, if we're talking about different categories of food, like Thai or Ethiopian, it doesn't make sense to subtract or divide those categories like their numbers. In our episode on variables and memory, we learned about data types, which are the different categories data values can belong to. In Java, certain simple and commonly used data types have particular names in code. For instance, integers are written as int and should only be used for variables which take on whole number values, because that's what integers are. For other kinds of numbers, we have a data type called double, which can store numbers that have decimal places, like 7.1. And when we specifically want the computer to know something is a piece of text, we use what's called a string. It's written with a capital S, as in string of text, although we often just call them strings. A string is technically a class, which is a different kind of structure in Java we'll cover another time, but for creating variables, we treat strings a lot like data types. In general, data types determine the kinds of data that go into or come out of a process, and in programming, the way we direct a computer to process bits of data is with expressions. In programming, an expression is a snippet of code that tells the computer to do a specific action on some piece of data in order to get a particular value, or output. Think of an expression as an order we're giving the computer where we want a single data value as the answer. Like telling a computer to add two numbers together and give the answer, or combine two pieces of text to make a new string. Both of these examples process data to create some kind of new data value, so they're both expressions. So let's get into the specific things an expression can do. If they're like the phrases of our code, we'd like to know what we can say with them. One simple task an expression can help us do is make a copy of some data. For instance, say we have a variable that represents one thing, and we want to use the same value it currently has in some other context. To see this in action, let's chat with Tino Tendo. He's getting ready to host a party, and he wants to make sure that he can offer top-notch hospitality. So he's writing some code to help take care of some of the prep, like ordering food and buying supplies. To set up his code, Tino Tendo creates a variable that represents the number of guests who are coming over. Now, Tino Tendo declares a new variable for the number of cups and sets the number of cups equal to the number of guests, copying that information. This variable will be handy if he needs that same number later in his code, like if he uses his code to total up the cost of all of his party purchases. Now, copying the value of a variable definitely comes in handy, but most of the magic of expressions comes from transforming data in some way. There are lots of ways to transform data, but in this episode, we'll focus on two kinds. First up, mathematical operations. The most common math operations are the familiar number crunching manipulations like adding, subtracting, multiplying, and dividing. These look pretty familiar across most programming languages. In Java, we represent adding and subtracting with the plus and minus symbol that we're used to, just like writing a mathematical equation. For multiplying two numbers in Java, we use an asterisk, and division is represented by a forward slash, the same symbol we use when we write fractions. Finally, there's an operator called the modulo, which gives us the remainder we get after dividing by a number, like 12 modulo or mod 5 equals 2. The modulo operator is represented in Java by a percentage sign. Tinotendo can use expressions like these in his party planning Java code too. For instance, to make sure he has enough dinners, Tinotendo declares a new variable called number of meals. He also declares a variable for the number of guests arriving after dinner, called number of latecomers, and this variable gets assigned a value. Now in his expression, he can subtract that from the total number of guests. He could have worked out how many meals he needed by creating an expression which just used values instead of variables, but there's an advantage to using variables. If someone calls to say they can't make dinner but will turn up later, Tinotendo can change the value of number of latecomers, and everywhere else in the code where number of latecomers is used, the value will change automatically. That saves him the trouble of working out every place in his code where the number 5 now needs to be changed to a 6. And it makes his code so much more understandable when he, or someone else, reads it later, because the code shows the logic of what numbers are being subtracted at a glance. Then, as he's writing up the code for the number of meals, Tinotendo realizes it would actually be way more helpful to calculate the number of lasagnas that need ordering instead of the number of people who need feeding. And for the expression that calculates the number of lasagnas, Tinotendo needs the number of vegan and non-vegan diners so he can order the right number of each kind. So he declares and assigns a new variable called number of vegan diners. At any rate, Tinotendo knows that lasagnas from his local pastaria, Zimmerman's Layers, feed about 6 people each, and with some math know-how, he can write an expression to tell him how many classic and vegan lasagnas he needs. The number of classic lasagnas will be the number of guests minus the number of latecomers minus the number of vegan diners, all divided by 6. He writes this out in code and runs it to see what answer the computer gives, but surprise, the output is 22 lasagnas! Since only 22 people in total are coming for dinner, the answer seems way off considering each lasagna feeds 6 people. But he quickly realizes the vital consideration he overlooked: the order of operations. Unlike reading a sentence in English, the computer doesn't always interpret the instructions in an expression sequentially from left to right. Instead, certain operations are given precedence or priority over others. For math operations, this hierarchy follows the same PEMDAS rules as in math. Everything in parentheses first, then multiplication, modulo, and division, and then finally addition and subtraction. So the issue in Tinotendo's code is division is done before subtraction. To fix his problem, all Tinotendo has to do is use parentheses around the bit of his expression he wants carried out first. And after making that correction, the code now returns 3 for the number of classic lasagnas, which makes way more sense and saves him from eating leftover lasagna for days on end. He might not like it, but I would. Anyway, now he needs the number of vegan lasagnas to order. For this, Tinotendo simply writes the expression number of vegan lasagnas equals number of vegan diners divided by 6. And after running his code, that comes out to 0 lasagnas. Mamma mia! The issue isn't that computers want vegans to go hungry, but rather it has to do with the second type of transformation expressions can do, which is turning one type of data into another. Crunching the same numbers on a normal calculator, Tinotendo would get a decimal or a fraction. Using common sense, he could interpret this as needing at least 1 lasagna for his vegan guests. But in his code, all of his variables, including the one he declared for storing the answer, were all integers. Java can't store fractions in an integer data type, so the code throws out anything that isn't an integer and returns a 0 instead. This also means that it's only by luck that he didn't run into the same problem in his classic lasagna code. In this specific case, even though he's already declared his variables, he needs to change them from integers into something else. And here's where expressions come in. We know that the output is not always going to be an integer, so we need the computer to see the variable storing that value as a different type, like a double, which can store fractions. But if he only changes the output type, the code still gives a 0 because his inputs are all integers. To deal with situations like this, many programming languages have a special tool: casting. In programming lingo, we can cast or transform an integer into a double by wrapping it in a line of Java code. Just like our other operations, casting can be a whole expression on its own, which takes a variable with some data type and returns a new value in a different data type. And you might wonder why we don't just go back and declare our variables as different data types. Well, when we first defined number of vegan diners, we gave it an integer data type since people come in whole numbers. So, to preserve that understanding, we cast the value of a variable when we need it to act like a double for some particular expression. This new code basically says that just in this expression, give me a double based on the value of this particular integer variable. Now when Tinotendo runs his code, he gets a decimal output of 0.666 and so on, which he interprets as meaning he needs just one vegan lasagna and might end up with some extra. And again, whether it's the order of operations or casting, the problems we just encountered results from a computer doing things exactly as we tell them to, since they have no idea what our variables represent. So it's really important to be explicit when we write code, and to make sure we keep testing our code to ensure it captures the process we want it to. But for now, Tinotendo can continue his meticulous planning in peace. While the simple math we've used might not seem like it warrants a computer, the general lessons we've picked up from here will form the bedrock of our programming powers. Just as we saw in Tinotendo's lasagna calculation, the magic comes from combining lots of different operations together in more sophisticated ways to tackle more complex problems. And there's a broader lesson about programming here. With familiar tools like math operations, we can break down a more complex problem into smaller, simpler pieces. If you're enjoying Study Hall Code and Programming for Beginners and are interested in taking an online course and earning college credit, check out gostudyhall.com or click on the button to learn more. Thanks for watching, and see you next time.